We're starting section 14.7, optimization in several variables. So first thing we want to discuss is local extrema. Then we want to do the second derivative test. As interestingly enough, we have a second derivative test with multivariables. And then we do optimization in 3 or more variables. That's the optional part. Most of this section is optimization with 2 variables, with 2 input variables. Then we do absolute extrema. Then we do the closed and bounded domain method. And so each one of these have an analogous part in calculus of one variable, basically. Local and absolute extrema. Let f of x and y be a function of 2 variables with domain D. A point A and B in D is 1. A local maximum if f of x and y is less than or equal to f of a and b for x and y near a and b. 2. It's a local minimum if f of x and y is bigger than or equal to f of a and b for x and y near a and b. 3. An absolute maximum if f of x and y is less than f of a and b for all x and y in D in the domain. 4. An absolute minimum if f of x and y is bigger than or equal to f of a and b for all x and y in the domain again. So some terminologies you know them from the past. Extremum is the plural of extrema. Means minimum or maximum. Global means the same thing as absolute. So if you see absolute max or absolute min, or global max or min, or global max, those are the same thing. The global is the same as the absolute. So let's remember the story of the Fermat's theorem. Fermat's theorem basically told us if there is a local min or local max, then the derivative and function is differentiable, then the derivative has to be 0 at that local min or local max. Now, let's use Fermat's theorem for multivariables. Suppose that f of x and y is differentiable and has a local extremum at a and b. Then the partial of f with respect to x at a and b is equal to partial of f with respect to y at a and b equal to 0. Equivalently, the gradient of f at a and b is equal to the 0 vector. So from now on, whenever I'm looking for local min or local max, I have to remember to set the gradient equal to 0 vector and solve, basically. Proof. Suppose f of a and b is a local maximum. Then imagine if you set one of the variables equal to constant. Set y equal to constant b, and because we want the direction to end up passing through point f of a and b, so set y equal to b constant, then this becomes f of x and b becomes a function of one variable. And so and also if f of a and b is a local maximum, this f of x and b is supposed to be a maximum at x equal to a. Yeah, because that's the point that is maximum on the surface. So any curve that goes through that point also has a maximum at that point. So by Fermat's theorem, for one variable function g prime of a or partial of f respect to x at a and b should be 0. And similarly works for partial of f respect to y at a and b. So you go down to by instead of going through the surface, you go through one curve that goes through x direction, one curve that goes through y direction, you realize each one of those curves have to satisfy the Fermat's theorem, and that's why there is the gradient has to be 0, because we're looking at those two directions. Now, definition: if gradient of f at a and b equal to 0 vector, then the point a and b is called the critical point of f. That's what we are basically we've seen in the calculus of one variable also. And there, though, you always solve for x. Here you have to solve for x and y, basically. All local extremas are critical points, but not all critical points are necessarily local extrema. Well, that was the same as calculus 1, right? As in calculus 1, we need a test to classify critical points as local maxima, local minima, or neither. The second derivative test. So you're expecting to see some test like you did in calculus of one variables, and this time first we have to introduce a concept called the discriminant of f at a point a and b in the domain of and so this concept helps you set up the second derivative test for calculus of multivariables. So let f of x and y be a function of two variables, then d of a and b, which is again the mixed part, it's the second partial with respect to x and x of a and b, and a mixed partial xy of a and b, then mixed partial y and x of a and b, and second partial f sub y and sub yy of a and b. Determinant of this matrix is going to be the discriminant. Again, by Clair's theorem, this mixed partials are the two mixed partials are the same if the mixed partial exists and they are continuous. So that makes f sub xy times f sub yx to be one of them to power 2, basically. And so this becomes the discriminant. Now use the discriminant to do the second derivative test. How do we use the discriminant? If a and b is a critical point of f and all second derivatives are continuous near a and b, then 1, if d of a and b is bigger than 0 and f sub xx of a and b is bigger than 0, then a and b is a local minimum. 2, if d of a and b is bigger than 0 and f sub xx of a and b is less than 0, then a and b is a local maximum. 3, if d of a and b is less than 0 this time, then a and b is a saddle point. And 4, as you're expecting from second derivative test, if d of a and b equal to 0, then the test is inconclusive. And so, and a few questions at this point will come to your mind. Why is it always d, for d of a and b bigger than 0, why is it always checking the sign for f sub xx? And here's why. Because if you're basically finding that d of a and b is bigger than 0, then what you know is that because this part is going to be negative, so this part has to be positive. So f sub xx of a and b times f sub yy of a and b has to be bigger than 0 to ensure that, at least, I mean, it works this way. that one implies that this is bigger than 0. Not always. If this product is bigger than 0, discriminant is going to be bigger than 0, obviously. But if the discriminant is bigger than 0, this product has to be bigger than 0. So when you're saying f sub xx is bigger than 0, and you know this product is bigger than 0, means f sub yy is also bigger than 0. If you're saying f sub xx has to be less than 0, and you need to know the product is less than 0, bigger than 0, so the other one has to be less than 0, sorry. So the sign has to match if the discriminant is bigger than 0. That's the main thing. So you just check one of them, and you know, because discriminant is positive, the other one has the same sign also. So the question at this point is why the discriminant is telling us so much information. It turns out, and sort of similarly to Calculus 1, or maybe a little differently, what we're doing in the second derivative test, we are basically trying whatever Taylor series are in calculus of multivariable, we use them to approximate the surface just in that local area, basically. And so you either approximating a surface with this type, with the ball looking up, just that tiny local area, or you're approximating with this one, which is a ball looking down, or you're approximating it with a saddle point, or you're not when it's inconclusive, you're not able to approximate or with the with any of these, basically. That's not how the test is not allowing you to know what you can approximate with, basically. So let's give this example and watch how the test work on each of the, give examples of each of these surfaces. The simplest example, one of the simplest examples of these surfaces, and see how it works. So for the first one, let's say z equal to x squared plus 4y squared. And I know that's a paraboloid, right? And I know paraboloids have, and this is paraboloid looking up, so the paraboloid has a local minimum. If I find the gradient for this one, so if I find the gradient for this one, number 1, the gradient of f is going to be equal to 2x and 8y. Setting 2x equal to 0, 8y equal to 0 gives me point 0 and 0, x equal to 0 and y equal to 0 is a critical point. So now we have to compute basically, and so let's say f of x and y is x squared plus 4y squared. You have to compute f sub x of x and y, which is, we just computed 2x, then f sub x, x of x and y, which is 2, then f sub y of x and y, which is 8y, f sub y of x and y, which is 8. What is left? We need an f sub xy. So let's see, this is f sub x. F sub xy is going to be 0. So d of xy is this term times that term, which is 16, and it's bigger than 0. And so the second derivative test works. And then I need one more piece of information. Either you're looking at fxx or fyy, but since we decided that the sign of them are going to be the same, I'm just looking at f sub xx. F sub xx, oh, sorry. So f sub x of x and y is equal to 2. I don't even need to plug in my critical point. I see that D and F are always positive. So the critical point is going to be a local minimum. And if you look at the shape right here, you know that there's a local minimum as well. Now let's do number 2. In here, f of x and y is negative 2x squared plus xy minus 3y squared, which is again, this is a hyperboloid looking downward, and it's the axis of the, basically the axis of the axis of the ellipses are a little bit off the xy axis. So now, and to be able to compute everything, first of all, I have to compute delta, a gradient of f, and that's negative 4x plus y, and x minus 6y, set it equal to 0, and again, this is, and if you are in linear algebra, you know that this is a system of linear equations. It's a homogeneous system of linear equation, and basically only a determinant of coefficients is non-zero, therefore only has one solution, and that's x equal to y equal to 0. But you can also solve it, and so that's the point. 0 and 0 is the critical point. Now let's find, so this was f sub x, this was f sub y, so let's find f sub xx, which is going to be negative 4, f sub xy, which is going to be 1, f sub yy, which is going to be negative 6. And there's an x, they're all functions of xy. X, y, x, and y. Now, form the discriminant. Discriminant is going to be this times that, which is 24. dxy is 24 minus 1 equal to 23. And so the discriminant 0, 0 again is 23. Bigger than 0, f sub xx as 0 and 0 is negative 4, less than 0. So the point is a local max. And as you were expecting. Now let's do the third one. And this time around, let's find the gradient first. It would be 8x plus y and x minus 4y. Again, if you set up 8x plus y equal to 0, x minus 4y equal to 0, because this is a system of linear equations with matrix of coefficients having determinant non-zero, this thing has a unique solution. Again, zeros on this side according to homogeneous solution. The homogeneous solution, unique solution is always 0. So the solution is going to be x0, y0. Then this is f sub x, this is f sub y. So f sub x, x of x and y is equal to 8. F sub x, y of x and y equal to 1. F sub yy of x and y equal to negative 4. So d of x and y is going to be negative 32 minus 1, negative 33, and f sub x is bigger than 0, but that doesn't basically concern us when we find the discriminant to be less than 0. Now the discriminant is less than 0, we have a saddle point. Now, what happens when d is equal to 0? So the second derivative test is completely, we cannot say either way that we have a local extrema or not at the point if d is equal to 0. And here are two examples. Example 1 and example 2. If you compute z equal to x squared plus y squared, y to the power 4, then the critical point is 0, 0. Discriminant is going to be 0, but the shape is like that, and there is a local minimum. If you compute this z equal to x squared plus y to the third, the critical point again is 0, 0, discriminant is 0, and there is no local min or max at 0, 0, as you see from the picture. So the last thing in this video, before we start the examples and why the test works, optional. Again, we kind of described that there were 3 options that you get when the discriminant is not 0. And those 3 options basically are there are 3 types of quadratic approximation locally there, and that comes from multivariable Taylor polynomial of degree 2. And that's why it's a second derivative test, multivariable of degree 2. Basically, and so when d is not 0, the higher orders of the Taylor polynomial are insignificant, and so the critical points actually behave with that degree 2 the higher degree of the Taylor series is going to be insignificant, so the polynomial of degree 2 best fits the approximation. When d is equal to 0, the test becomes inconclusive because we don't know how the higher orders are going to work. And so the next video is about examples.